Dear students, welcome to the next lecture of wireless communication. So today in this lecture we will start communication networks. So when you talk about wireless communication or any communication as such, we are mainly a part of a big communication network. Okay, so the notion of communication that you have so far is basically point to point communication where you are you are communicating between one point to the other, from a transmitter to a receiver. Now if you have many such communications that are happening from one point to other and from the other point to the next, then you form a network of such communications. So a close example will be the network of communications between, let's say, cities. Okay, so you go from one city to another and then from another city to the other. So you have a road network that connects the different cities. Similarly, you have a communication network that connects different points from where your data is getting originated, and um, it's reaching its destination. So the internet that you are using is made up of many such communication networks connected to each other. Okay, so before going to the details of communication networks, so let's see what this slide actually tells you. So communication network can be a very small scale, like within a very small area, and each point of communication can be very close to each other or it can be far apart. So let's say you are connecting a few different computers together. Okay, each one having a processor. So you are setting up a multiprocessor, so where all the nodes or all the computers uh, which are part of the multiprocessor are very close together, of the order of a few hundred meters. So in that case you call it a multiprocessor. So you see you have, like, it's between 1 meter to less than 1 meter, so they are very closely spaced, and then they can achieve very high speed communication between them. Data can move from one point to another at let's say 10 to the power 6 bits per second to 10 to the power 8 bits per second. And then you can have local area networks. So you can have traditional local area networks, and an example can be the campus local area network that you are using. You can also have high speed version of the local area network, so they are between, let's say, 100 meters to a kilometer range. And then you have the metropolitan area network, so these are between, let's say, one city to another. So typically their range is between kilometer to uh, hundreds of kilometers. Okay, and then you have the wide area networks, which are even larger area. So these actually um, are countrywide. Okay, so let's say an entire country, uh, the entire of China can have, let's say, its countrywide wide area network. And then speed wise also, these can be like different types. So for example, traditional wide area networks can be having speeds of 10 to the power 4 to 10 to the power 6 bits per second, but you can also have high speed variations of wide area networks as well, with speeds more than 10 to the power 6 bits per second, up to, let's say, 10 to the power 8 or 9 bits per second. So moving on, let's look quickly into the different characteristics of wide area networks. So as I just said, it covers large geographical areas, for example, a country or a continent. and the circuits are provided by a common carrier. So when you say circuit here, this means it's the is the communication lines. Okay, so it's not the circuit that you mean from your circuit theory background. Okay, so these circuits here means the end-to-end links, okay, that are set up for the purpose of sending data. Okay, so these circuits, these are provided by a common carrier in a WAN. So common carrier means the company that provides you the connectivity. So let's say China Telecom or AT&T, like this. And this consists of interconnected switching nodes. So these switching nodes are basically located in different cities. Okay, and they are interconnected through different circuits, and data can be communicated between each of these switching nodes. And then the traditional WANs, they provide modest capacity but high speed ones. They use optical fiber and other technologies like ATM to provide higher speeds. Okay, um, even in the range of gigabits per second, not only megabits per second, but maybe in the range of gigabits per second also. Then comes the characteristics of a LAN. So in LAN, you are, when you're talking about LAN, you're talking about a smaller area. So LAN interconnects a variety of devices and provides some means for information exchange, but then they are within a smaller geographical area. Okay, and traditionally the LANs used to provide between 1 to 20 megabits of data rate, but we also have high speed variation of LANs also, because of enhanced technologies, and we can reach up to 1 gigabits per second. Now the difference between a LAN and a WAN, as you see, the scope, okay, the geographical reach or the scope of a LAN is smaller because LAN interconnects devices within a single building or a cluster of buildings, and is owned by the organization that owns the attached devices. So um, the the BJUT campus LAN is owned by BJUT itself. Okay, but for WANs, most of the network assets are not owned by the same organization. So if you consider the countrywide WAN of let's say China, the different switching nodes and the connection links, they can be owned by multiple organizations. Okay, uh, it can be the government and private organization. It can be many private companies together. So this is the difference. And then the internal data rate of LAN is much greater, okay, compared to WAN. So you can have a very high speed LAN within a building. Okay, now let's focus on the switching terms. So you came across the term switching nodes in one of the previous slides. So basically these are intermediate switching devices that moves the data, and they are not concerned with the content of the data. Then we have stations, which are end devices that wish to communicate, and each station is connected to a switching node. Okay, so your end station can be your laptop. Okay, this can be your laptop or your smartphone, and then these or your tablets. Okay, these are your end stations which are connected to the nearest switching node. The nearest switching node can be your uh, wireless LAN access point. Okay, so and then this access point provides you connectivity to the rest of the internet. And the communication network, as we were saying, is a collection of these switching nodes. Okay, so we will see that in this slide. Okay, so let's say this is a communication network. So here you have like 1 2 3 4 5 6 7, so 7 switching nodes. So each of the switching nodes are connected through some links. Okay, these black lines are the communication links. So these can be uh, optical fiber links, or it can be wireless links. Okay, depending on how close these switching nodes are. If these switching nodes are a part of a wide area network with large geographical coverage, uh, thousands of meters, or hundreds of kilometers, then these will be optical fibers. Otherwise, if they are close by, this can be achieved um, through wireless communication also. Okay, so so these links can be wireless or can be wired. And each of your end stations, so these are your end stations, this can be your personal computers, this can be your mobile phones, this can be a big server, anything that has an internet connectivity can be an end station. And these end stations are attached to your switching nodes, and the switching nodes form the network. So this is the entire network, whichever is shown within this blue cloud. And these switching nodes and links, they form the entire network, and they provide connectivity between the end stations. So let's say if A wants to connect to B, then you can have a path from here to here. Okay, so going through the switching node 4, then to switching node 1, and finally to B. Okay, if again A wants to connect to, let's say, F, then you have to go through, let's say, here, and then through this switching node 7 to this switching node 6, and then finally to F. Okay, and then you can have alternative paths also. Let's say the same path between A to F, okay, can be formed by, let's say, this way. So we can go through 5, and then through 6, and then here. Okay, so basically you can see the similarity between this network and the road network. Like if you want to go from one city to another, you might have multiple options. Okay, you can take uh, one route, and then you can take an alternative route also. Okay, so similarly in communication network also, the data can be moved uh, between multiple routes. So as you can see, between A to F, you can have two routes in this example network. So so this is the scenario. Okay, now when you are establishing a connection, there are different techniques that are used. Okay, to establish that connection. Okay, and two most prominent ones are circuit switching and packet switching. So circuit switching means it's a dedicated communication path between the two stations. Okay, for example, the public telephone network. Okay, and for packet switching, the entire message that you are trying to send is broken into a series of packets. Okay, and then they are dispatched, and each node determines the next leg of transmission for each packet. Okay, so this circuit switching is like, let's say you have a dedicated path between uh, two nodes. Okay, or two stations. So let's say you are going to go from Beijing to Shanghai, and you have a fixed path or a fixed road. Let's say you want to go from Beijing which is here, to Shanghai, and you have a dedicated road. So this is the example of circuit switching, and whoever wants to go from Beijing to Shanghai can take this dedicated road and go by a car or by a bus. All right. In case of packet switching, you you have a message to transfer, let's say between Beijing to Shanghai. You break this message into different packets and you form, let's say, envelopes. Okay, put your message into this envelope, and then you send by post between Beijing to Shanghai. Okay, and let's say your your series of packets reach Beijing to Shanghai through different routes. Like you can take uh, not only a single route, but you can take different paths, and even the different packets can be numbered like 1 and 2, and one packet number 1 can take this path, packet number 2 can take this path, and then in Shanghai you received all these packets and then read the message that is contained in these packets. Okay, and intermediate nodes in the network, like let's say here is another city that can receive these packets, let's say, and depending on the address written on these packets, okay, this intermediate city or intermediate node will, find out what will be the next destination. So let's say the address written here is Shanghai, so this city will know that these packets are meant to be sent to Shanghai, and then it will send to Shanghai. Okay, so each node determines the next leg of transmission for each packet. Okay, so this is the fundamental difference between circuit switching and packet switching. So this is an example of the telephone network. So you have uh, you have dedicated paths between, let's say, this point and this point. Okay, you have a local exchange, then you have the inter-exchange carrier, you have the point of presences, and you have the central offices. So the local exchange, when you are trying to establish a call from this point to this point, it will be first handled by the local exchange central office, and then it finds out a path through the entire network. Okay, uh, finds out a dedicated path. So this is actually circuit switching. So this can go like this. Okay, so you see these are all dedicated paths, and any of these can be taken. Okay, um, so this is circuit switching. uh, so let's say what are the phases of circuit switching. Okay, so you have the circuit establishment, where an end-to-end circuit is established through your switching nodes, just as you saw in the previous example. Okay, so it's basically uh, trying to establish an end-to-end circuit. So here we have an end-to-end circuit. Okay, that is established between the local exchanges central office and the IXC point of presences. So all these intermediate nodes are taking part. Okay, to to all these switching nodes, all the intermediate switching nodes are taking part to establish the end-to-end circuit, and then information is transmitted through the network. And this information may be analog voice or digitized voice, or it can be binary data. And then once you finish the information transfer, then your circuit is disconnected. Okay, so the circuit is terminated, and each node deallocates the dedicated resources. Okay, so whatever switching was happening, all the switches, they become free to establish the next circuit once the information transfer is finished. Okay, so so this is circuit switching. And When you talk about the different characteristics of circuit switching, the first thing is that it can be inefficient. Why? Because the channel capacity is dedicated for the duration of the connection. Okay, so the entire circuit is blocked. Okay, whenever, as long as you are talking between these two telephones. So let's say this is you, and this is your friend. Okay, and let's say you are discussing uh, about a movie that you recently watched, and you are talking about the entire movie, and you are talking for more than half an hour. Okay, so for this entire half an hour, this circuit that was dedicated for you and your friends conversation is blocked. Okay, nobody else can use this circuit, or nobody else can use the resources, the switches that are involved in establishing this circuit. Okay, so that is an inefficiency. So that is an inefficiency. Okay, channel capacity is dedicated for the duration of the connection, and you cannot utilize it fully 100%. So let's say uh, this circuit has a very high capacity. Okay, but you are only transferring voice message through it. Okay, so you are not fully utilizing the capacity of this circuit. Okay, or in other words, imagine that this is a road. Okay, this is a this is a 4-lane highway. Okay, and you are only driving one car through one of the lanes of this highway, and the remaining are getting wasted. Okay, remaining resources are getting wasted. So this is not, again, 100% utilization. Okay, if you were, let's say, playing an online game, let's say using your smartphone between you and your friend, then that probably would use more capacity, and that could be 100% utilization of this circuit. Okay, but if you are only doing voice communication through a circuit like this, which has more capacity than you are using, and that too for the entire, let's say, 30 minutes of your call. Okay, then you are basically wasting the resources. Okay, so this is what is meant by utilization is not 100%. And there is a delay prior to signal transfer for establishment. So before you actually start talking, the circuit establishment phase has to occur. Okay, as you saw as you saw the first phase of circuit switching is this circuit establishment, and this will take some time before you actually start talking, or try to transfer the information. So that's why there is a delay prior to the signal transfer for establishment of the circuits. So, but once the circuit is established, the network is transparent to the users. So you can have full connectivity once the circuit is established, and the information transmitted can be only at a fixed data rate, and with only propagation delay. Okay, so this is something which is different compared to packet switching. So when we will study packet switching and go through its characteristics, we will be able to appreciate this part. Okay, that what is meant by the information is transmitted at a fixed data rate with only propagation delay. Okay, so so one example of a circuit switch network is the public telecommunication network, or the landline telephone network. um, so you can have subscribers. Those are the devices that attach to the network, mostly the telephones, the landline telephones. Okay, and then you have the subscriber line, which is the link between the subscriber and the network. This is sometimes also called subscriber loop or local loop. And then you have the switching centers called exchanges, which actually support the subscribers and a switching center that supports the subscriber is also called end office. Okay, and then there are trunks, which are branches between the exchanges. Okay, so so these are the different components of a public telecommunication network. And then this is how an example connection over a public circuit switch network operates. So you have your telephone here that is getting connected to the end office. The end office is getting it connected to the long distance office. And this is like, these are intercity offices, long distance office. It connects you to the next long distance office in the next city. The long distance office is now diverting your call to the end office where your final subscriber is attached. Okay, so so now coming to the packet switching. So how packet switching works? Again, as I briefly mentioned, so packet switching means your data is transmitted into small packets. Okay, and before sending, the message uh, is broken into actually a series of such packets. Okay, so let's say you have a long message like this, the application data, and you break them into three small packets. Okay, and packets are typically of the length of 1000 octets. So octets also means bytes basically. And then each packet contains a portion of the data plus a packet header. Okay, so this packet header actually includes control information. So this is nothing but uh, the information that where these packets will be delivered. Okay, so this is kind of the address. Okay, if you imagine that these packets are postal packets. Okay, when you break your message into small postal packets like this, you also put your address here. So these headers are basically these addresses. So when you are sending these packets through the packet switching network, each intermediate switching node in this packet switching network will read this address, and then it will forward it to the next node, and finally it reaches the destination. Okay, so as I just said, at each node in the route, a packet is received, stored briefly, and then passed to the next node. And when it is stored, this address in the packet is read, and then it is passed to the next node. And this address is contained in this header. Okay, each packet has a header. So now let's talk about the advantages of packet switching, and here you will be able to find out what are the differences of packet switching with circuit switching. So let's say in case of packet switching, your line efficiency is greater because you are sending many packets over time and they can share the same node to node link. Okay, so now again, if you revisit the road analogy, okay, so let's say you have split your packets data into small packets like this. Okay, let's say this is packet 1, this is packet 2, and this is packet 3. And packet 1 moves in a car which is taking this lane. Okay, packet 2 moves in another car which is taking this lane, and packet 3 is contained in another car which is moving in this lane. So you can utilize the entire capacity of this road. You are splitting this message into different packets, and those packets are traveling towards your destination in different cars, let's say. Okay, and you are using the entire capacity of the road. Okay, so compared to circuit switching where you had the 3-4 lanes of the road, but you are moving only in one car. Okay, and the remaining capacity was getting wasted. Okay, so many packets over time can dynamically share. So share, this is the important term, share the same node to node link. Okay, they can share the same roadways. Okay, um, if you imagine your packets to be sent over different cars. Okay, so now packet switching networks can carry out data rate conversion also. So two stations with different data rates can exchange information in packet switching. So let's say if you are breaking the message into packets, and let's say if your source node A is sending at a higher rate. Okay, let's say your source node is sending uh, 3 packets at a time. Okay, and your destination node, let's say B, can receive only 1 packet at a time. Okay, but this is still okay. Okay, the other 2 packets will be stored in a buffer. Okay, and wait until the reception of this 1 packet is complete, then the next can be received. But in circuit switching, this is not possible because you have a dedicated circuit, and whatever rate the source is pumping data, that rate has to be also there in the destination uh, for receiving the data. Okay, so two stations with different data rates can still exchange information because packet switching networks can carry out data rate conversion. So 3 packets per unit of time can be converted to 1 packet per unit of time, and the remaining can wait in a buffer. Okay, and unlike circuit switching, networks that block calls when traffic is heavy, packet switching still accepts packet but with increased delivery delay. Okay, so again, if you imagine circuit switching, which is like let's say a dedicated road between two cities A and B, if you consider circuit switching as this example, then if this road is blocked, then you cannot do this communication. Okay, but in case of packet switching, you can still accept the packets. Okay, uh, but then they will be delivered with a delay. Okay, so that means uh, let's imagine the case of again the postal system. Okay, let's imagine your packet switching is similar to the postal system. So you are sending your data in different small packets. Okay, like this with some addresses here. Okay, now the post office can accept all your posts, and depending on the next available route, it will send your packets to your destination with some delivery delay. Okay, so that is possible. But in case of circuit switching, you have established a dedicated road, and if that road is busy delivering other communications, then you cannot use this road. You have to wait until this road becomes free. Okay, so that's what is said here. Unlike circuit switching networks which blocks the call when your traffic is heavy, packet switching still accepts packets but with increased delivery delay. And in packet switching, you can use priorities. Again, this is similar to the concept of postal system as well. So if you are paying more to the post office, and if you are doing registered post, let's say, or speed post, then your your speed post parcels or your registered post parcels will given higher priority. They will be delivered fast than your regular post. So these priorities can also be used in case of packet switching. So we saw the advantages of packet switching. Now what are the disadvantages of packet switching? So each packet um, each packet switching node introduces a delay. So the packet goes from one node to other, And let's say during the journey of your packet, let's say this is your source and this is your B destination, and your packets are moving from here. Okay, so let's say it goes to an intermediate node C, and then it goes here. Okay, so whenever these packets arrive at the intermediate node will read the headers, okay, that's are there in the packet, or let's say the addresses in the packets, to decide that these packets will be moved to node B next. Okay, so this process of reading these headers or reading these addresses will take some time, and that introduces a delay. So overall packet delay can be very high or it also can be very low, okay, depending on how many packets you are sending and how much time the intermediate nodes are taking. So this introduces a jitter. Okay, and this is caused by different packet sizes, the routes taken, and varying delay in the switches. Okay, so so this is something which is a disadvantage of packet switching. Okay, and then each packet requires overhead information. So as I said the packets need some header or some address. So this reduces the communication capacity. Okay, if you need to have, let's say each packet, or let's say the entire message is 100 bytes. Okay, and you decide to divide it into 10 packets, okay, of 10 bytes each. Okay, so each of these is 10 bytes, and then you decide to put some header. Okay, so let's say 1 byte of header is there for each packet. So essentially every packet will have 1 byte extra. So instead of 10, every packet will be 11 bytes. Okay, and you have 10 such 11 bytes, so that will add up to 110 bytes. So to send a 100 byte equivalent message, you end up sending 110 bytes. So this 10 is the overhead information, and that can reduce the communication capacity. As you see, instead of sending 100 bytes, you are sending 110 bytes. So that is something which you are sending extra, and more processing is required at each node. So as I just said, each node takes some time to receive these packets and then store them temporarily, read these addresses in the header, and then decide to send it to the next node. So this takes some processing, and more processing is required at each node. So this is again a disadvantage of packet switching. So when we talk about packet switching, we have again different types. The first type is called datagram. So in the datagram approach, each packet is treated independently without reference to previous packets. Okay, and each node chooses the next node on the packet's path. Uh, Packets don't necessarily follow the same route and may arrive out of sequence. And the exit node restores all the packets to original order. Okay, so and then it's the responsibility of the exit node or the destination to detect loss of packet and how to recover. Okay, so let's again think about this as the postal system. Okay, so your your source node is sending some packets, okay, in this form. uh, okay, let's say an entire message is broken down into three packets, and they are put in an envelope, and they are put some addresses here, and then they are sent using packet switching. Okay, so in the datagram approach, each packet is treated independently without reference to the previous packet. So let's say you number these packets 1, 2, 3. Okay, and then The packet 1 can be traveling through an intermediate node C. Okay, let's say this is the packet 1's route. Then packet 2 can reach through another intermediate node D. Okay, so let's say this is packet 2 going, and then packet 3 is going through another intermediate node E. Let's say this is the route of packet 3. Okay, and whenever this node receives this package, the intermediate nodes, let's say C receives 1, it treats this packet independently without reference to the previous packets. Okay, um, or let's say 1 is 1, but let's say 2. Okay, let's say the intermediate node D receives packet 2, so it doesn't care that the number of this packet is 2. Okay, and there was a 1 numbered packet that might be somewhere. It doesn't care about that, it just receives this packet 2 without reference to the previous packet and chooses the next node on the packet's path. So D receives packet 2, and by reading the address on packet 2, it chooses, or it decides that the next node is B. Okay, and it sends it to B. And it's the responsibility of this final destination node or the exit node to restore all the packets 1, 2, 3. And if it has not received any of the packets, then it has to wait, or it has to decide whether that packet is lost, and how to recover that packet. So this node is responsible for everything. So this node has to wait until it receives 1, 2, and 3 from different independent routes, and then it, you know, merges all the packets together. Okay, 1, 2, 3, to make a combined message. Okay, like this. So the advantages of this datagram approach is that the call setup phase is avoided. Okay, and because it's more primitive, it's also more flexible. Okay, and the datagram delivery is more reliable. Okay, so another approach of packet switching is called virtual circuit. Okay, so here first you have a pre-planned route that is established before sending the packets. Okay, so this establishment of a pre-planned route is similar to circuit switching. Okay, so that's why this is called virtual circuit. Okay, so this is still packet switching, but the path that the packets will take is decided beforehand. So that's why it's called virtual circuit. All packets between source and destination follow this route. Okay, so unlike the previous example where different packets were following different routes, so this was a route, this was another route, and this was another route. In case of virtual circuit, you uh, you decide a route, and then all the packets are going through that particular route only. And routing decision is not required by nodes for each packet. And this emulates a circuit, as I said, in a circuit switching network, but is not a dedicated path. Okay, so let's see a visual example that will be more uh, clear for you. So let's say this is the packet switching for datagram versus virtual circuit. So here you see this is the datagram approach. Okay, so in this approach you start with this 1, 2, 3 sequence of packets. Okay, and then the route that these packets follow are different. See, here your 2 and 1 gets splitted in this direction, and your 3 gets another direction. Again, at this node, your 1 is getting splitted in this direction. Okay, um, your 2 is also getting in this direction, and then 2 and 1 follow this route and reaches here, but 3 follows another route and then reaches here in the end node, and the end node then actually sequences all the packets together 1 to 3 and sends to the end user. Okay, so let's imagine that this is the post office of your destination city. So you are sending some packets from Beijing. So this is you, and let's say this is your friend, and you are sending some packets. You are sending a message to your friend in 3 packets. Okay, so these 3 packets are getting received at the destination city, let's say in Shanghai, and the post office in Shanghai receives all the packets, and then it actually orders them together and then sends to your friend. Okay, so this is the datagram approach. Here is the virtual circuit approach. In the virtual circuit, first you establish a predefined route, okay, as denoted by this dotted line. Okay, so this is your predefined route. Okay, similar to the circuit switching approach, but then this is not exactly packet switching. Sorry, my apologies. This is not exactly circuit switching. This is still packet switching, even though you are establishing this predefined route. You are sending the packets in sequence. Okay, 1 2 3 all are taking this route itself. They are never getting splitted, for example, here and here. Okay, it's always taking this predefined route, but then the message is still broken into 3 packets, 1 2 and 3, and every node receives these packets and determines which will be the next node. So let's say it reaches from this node to this node. This node decides what will be the next node where these packets will be sent. Okay, so let's say the next node according to the virtual circuit is this, because you have a predefined route. So this node again receives all the packets, and this node now determines based on the addresses here and the predefined route that this will be the next node. So now all of the packets reach here, then similarly all of the packets reach here, and then it reaches the final destination. So this is the difference between your datagram approach and virtual circuit approach. Both are packet switching, but datagram uh, doesn't have a predefined route. Okay, it can take different routes independently, and then at the final destination you you reorder your packets and send it to the final end station. Okay, so let's talk about the different data transmission modes now. Okay, so so you can have a simplex communication where your communication takes place in one direction only. Okay, from A to B only, let's say. An example of this is TV broadcast, where your TV station is A and it is sending the TV signals uh, the to the receivers that you have in your house. Another mode of transmission is half duplex. So here the communication takes place in both directions, but only in one direction at a time. Okay, and this is this an example of this is a walkie-talkie. So if you have seen different security personnel or police, they talk to each other on a walkie-talkie. So when one person talks, let's say in this direction between A to B, the other person has to wait, and when this person finishes conversation and says over, then the next person starts talking. Okay, so you might have seen in movies also. So you are talking, one person is talking, and then that person is saying over, and then the next person starts talking. Okay, so this is half duplex. And then you have full duplex, where communication takes place in both directions at the same time. So this example is telephone line, where let's say you and your friend talking on the telephone can simultaneously talk to each other. Both of you are talking together at the same time. That can happen. So, so you might wait for your friend to finish what he or she is talking, and then you talk. But ideally, both of you can also talk together. This happens quite often when basically you are fighting or quarreling over a matter. You tend to talk together. So that's actually an example of full duplex communication. But the question is, do we have real full duplex? I want you to think over it. Okay, like, do we really use the same communication line for both way communication? Uh, I want you to ponder over this and tell me in the next interactive session. So I will stop here, and then maybe in the next class we will start with network topologies. All right, thank you.